We're a bit late. We were trying to get some people. I think there are a lot of traffic jams around, and maybe people are delayed on the way. But we cannot stop now. We will have to start the session. So, good morning. Let me introduce here one Mr. H.G. Kulkarni. He will be chairing the session for this session. He has a vast experience in heat treatment, and he is one of my guru also. He has around 45 years of experience in heat treatment field. It's varied from gear technology, gear heat treatments to now he is doing heat treatment of sheet metals for defense requirements. So that varied experience he has in heat treatment field. He has worked in many organizations as head of organizations, as director of organizations, to name a few. Bharat Gears Limited. Then the recently one is RSB Transmission. Then he is a consultant in heat treatment also. So let me invite H.G. Kulkarni to chair this session. Thank you very much.
Thank you, Sandeep, for your kind introduction. We'll get started. Already we are behind schedule, so I think. Hello. Hello. We'll get started with the session. Already we are behind schedule, but I think we'll start immediately. We have a very new technology development session this. Including additive manufacturing, and we have got speakers with very good background. The first speaker of the session is Mr. Srinivas Raghavan. I'll just give a brief introduction. He's with Singapore Institute of Manufacturing Technology, Singapore, as senior research fellow. He has done PhD from Purdue University, USA, and MTech from IIT Kanpur. I will request him to get started with this session. I think we should sit there. Please. 10 minutes, I'll give you a call, and then in 20 minutes we have to finish.
Hello, thank you. Firstly, I would like to thank the organizers, ASM, Dr. Sudarshan, for inviting me and giving this talk. So I'll be talking about additive manufacturing from defense, and I'm from Simtech A-Star. But A-Star is not related to defense, and in the sense they don't make any products to defense or anything. So I'm not endorsing them in any of the slides. So this is all the slides which I have prepared. So the outline of my talk would be, I'll give an introduction about additive manufacturing and all the statistics related to it. I'll just briefly touch upon the different additive manufacturing technologies. Then actually present the different case studies or the examples which are used for defense sector. Then moving on, I'll be comparing the mechanical properties of the AM parts as compared to the traditional manufacturing, cast and forged and all that. Finally, future directions on making the AM more inclusive or more popular, how to go about it. So additive manufacturing, as per the ASTM definition, like what John had given yesterday, it's basically defined as joining of materials layer by layer, where the input is directly taken from a 3D model data. It is different from the traditional manufacturing, which is subtractive manufacturing, because to come to the near net shape part, you have to do a final machining and everything. So in this, you do some machining to have a good surface finish, but what you get is a net shape part in the end. You feed a CAD model and you get a part outside. So Obama actually in 2013, he declared that 3D printing is going to revolutionize the world. And I think it is living up to the hype. It is just growing rapidly, additive manufacturing. And he has set up all the additive manufacturing centers that America makes. It was also voted as one of the 10 breakthrough technologies by MIT Technology Review. So just to give a snapshot of additive manufacturing, so you have a CAD model, and it is actually, you feed it in a STL file, which is a typical a 3D printing file. It's called stereolithography file. So the file actually, it slices all the information layer by layer, and which is actually given to the equipment or the machine. So then it starts printing layer by layer, and you get the final product. So the advantage is you can have any complex design you want in the model, in the design model, and you can get that out. So you can get a complex design. If the component requires extensive machining, it's better to go with additive manufacturing. So it has also the potential to reduce the weight, because you can come up with new designs which are strong but lightweight, like some structures, lattice structures or porous structures which are strong, but you can go to a lightweight design. And also the assembly of parts also can be reduced, because usually they assemble different parts to get a final complex shaped part. But in this, you can directly manufacture. So you can have a reduced number of parts on a single part. So the buy to fly time ratio also is good, and the speed time to market is fast. It can be termed as on-demand manufacturing, where you put a demand with a design, and then you can get the part out. So some of the statistics, I'll just briefly go over through this, because you can find it online, how the additive manufacturing is going to grow to about $22 billion by 2020. And most people believe that, the aim is going to be ubiquitous and standard in next 20 years. It's going to be the one. And different applications of 3D printing. And as far as aerospace and defense, the current revenues are about $140 million. And it's going to grow to $600 million in 2022. So when you look at by country, the government spending, I put it here. Singapore is, they're spending heavily. It is part of advanced manufacturing techniques. So they have some, apart from additive manufacturing, any other manufacturing like, robotic welding, robotic machining, all those things are one. It also comes into the same package. US, only NAMI is giving about 50, and there are other investment in defense and Navy and all that, which I couldn't get the figures. But I think right now, this is in 2014, right now it is spread more. Many other countries have joined this bandwagon of additive manufacturing. I'm not sure, in Indian government, I think still has to get into this to start this. As far as the number of machines is concerned, the total, since the US, it's a big country, there are a lot of, the maximum number of machines which are being introduced are in the US. So I'll just briefly touch upon the different additive manufacturing. To start with the plastics and polymers, and then go to the metals. So the first is a VAT photopolymerization. It's also called as stereolithography, where you have this ultraviolet curable liquid resins, which is put in a tank, and you have a laser or ultraviolet which scans across based on the 3D model. And the whole thing, once it's scanned, once it is set, it's lowered down to go to the next layer, and again scanned. So it just keeps going on, and you get a final net shape part. So the advantages and the problems are here. It's usually very accurate, very fast, but very limited materials in this. It's also an expensive process. Traditionally, many of the plastics are used for prototyping, because once you get the final design in prototypes, then you can quickly make the same design in metal parts and all that. So it has been used for prototyping, and sometimes the casting patterns and everything. There is a binder jetting process where you have a powder. It can be a metal powder, it can be a ceramic powder. Then you actually jet a binder. You scan across layer by layer. So then you get a green compact. It binds the contour, then you get a green compact. Later you remove the powder and then you have to do a post-processing of sintering, then heat treatment and all that. So this is a much longer process. It requires post-processing, curing and all that stuff. But this can be applied to ceramics as well. It can be ceramics, composites, even metals. We have a binder jet process. And also one good thing is if you make a porous design, you can do a hybrid materials. You can infiltrate with a second material. Like yesterday he was talking about having a steel and infiltrate with bonds, and then you get a hybrid materials. Then there is a sheet lamination. This is, I think, relatively less popular, but it's about you have a sheet, then you have a laser or something which cuts across the layer by layer on the sheet, and the next sheet comes and binds on the top, and then the whole thing gets built up. Material extrusion is like fuse deposition modeling. You have a wire which comes. It can be applied to the both plastics and metals. The wire is melted, and then it's scanned layer by layer. Then you have a material jetting process. Like binder jetting, you can directly jet the material. It's like a inkjet printing or something. You have material there. For metals, the most popular ones are the powder bed fusion or the powder feed. The direct energy deposition is also called the powder feed process. So in the powder bed, you have a powder bed and you have a laser which scans layer by layer, and then you build the whole part. In the powder feed, the energy, thermal energy, like the laser or the electron beam and the powder, they're all fed into the same spot. And then the melting and the fusion happens there. And then the whole part is built up. So, I mean, it's because you have a very small powder size, typically about 40-50 microns, and then you have the laser spot size also very small, so you can actually build really complex, thin-shaped parts through these processes. Okay, now I've just given you some of the advantages and also scanned upon the different technologies. So what are the main challenges now to go to the AM? So now once you build a AM part, the certification of parts is necessary. There are very few standard certification companies which actually have a proper standards in place to certify the parts, both the quality standardization for the finished parts and also the powders. And there are some legal IP related issues also. Suppose you have the same design which is printed to 3D printing or printed to traditional route. So how the conflict is resolved. So then, of course, the cost of the equipment is very high in the initial investment. There are slow printing times, and you can just go through the list of the challenges which have been for the additive manufacturing to go mainstream. So here for defense, the advantages or the attributes of additive manufacturing to traditional manufacturing is pretty similar. The advantage is pretty similar to what I've discussed before. Because in defense, you get all to manufacture the complex shape design parts, and you have to come up with a new design each time because the technology is improving every time. You have to come up with the new designs of parts, customization to customer requirements, ease and flexibility of design, part simplification, reduce time to market because it's like on-demand manufacturing. There is a waste minimization. That's why it's supposed to have high buy-to-fly ratio. The amount of material you put inside and what amount of material which you take out in the product, it's almost the same because there's not much wastage. So, I mean, how the supply chain works for additive manufacturing as opposed to traditional manufacturing is over here. So in the traditional manufacturing, there are many steps. You have to manufacture different parts. You have to do an assembly. Then you have to store it in a warehouse. And then, then whenever you distribute based on the demand. So at many times, the lot of parts which are stored in the warehouse, because the whole process, the steps are so time consuming, they keep it there. And it goes waste also, because any new design comes up, it becomes obsolete. So additive manufacturing that way can have a localized production. I mean, it's an on-demand production. Okay, now you want this design, you want to produce this, you give it and you get it. So definitely the supply becomes much leaner, the supply chain becomes much leaner without much wastage or storage of the parts. So that's it. So for the examples where the additive manufacturing parts have been introduced in defense and aerospace, this has been, yesterday it was told by John. So this is the first critical component which seemed to have been introduced in a V-22 Osprey flight for US Air Force. Yeah, is it US Navy, I think. It's a US Navy flight. This is actually a link which connects between the engine and the wing alloy. So this is a critical component because if this fails, that's it, the whole aircraft has to be stopped down. So this is, I think, one of the first instances where a titanium part has been manufactured and been employed in the flight. Huh? 5 minutes? Okay, sorry. And okay, there are many more examples like the Royal Air Force, British Air Force flies Tornado with 3D printed parts. All the list is given here. They also come up with the first 3D printed drone, which is tested by Royal Navy. And I was also talking about on-demand manufacturing. So many of the nuts and bolts which are actually high-demand parts. And it's very hard to ship them to all the military bases because of the design. So many of the US Air Force, they have put up some machines to produce them locally whenever it's needed, and so the lead time is reduced drastically. So there is also this fully additive manufactured gun. Again, the advantage has been it's very nice design, reduced parts. Yeah, so that's. For plastics, I think the prototyping is the most popular way of additive manufacturing. So whenever they come up with a new design, new mask ensemble with different parts. So additive manufacturing prototypes have reduced their time, they reduce the cost, from 6 weeks to 3 weeks, 6 months to 3 weeks. So once they get the prototype, they go about producing the final product with any traditional route, which is, if there's large numbers, it becomes cheaper making through traditional route. So I'm just giving the different examples. It's quite similar in the valve stem cover, sensor holder, where the lead times are reduced. So the dust caps for radios, it's fast, it's economical for plastics. The mounting brackets for mine detectors is another example. Again for plastics. So this is another case where, it's another case where the OEM was no longer making this part, and now but still they have the design from that. So they just quickly use the additive manufacturing to make the circuit card clip for submarine assembly. And many of they're also going about installing the AM machine in the ships or in the all the requirements which is required in their ships or submarines and all that. So it can be catered through additive manufacturing. So the other thing is embedding sensors, like Dr. Sudarshan was saying yesterday, making your helmet or the headgear more smarter, so you can embed the sensor for better communication, for better information, you can get it. So this is also, I think it's going on in the US Department of Defense. For additive manufacturing casting cores, that is quite common now, even defense and also outside. There is a lot of time savings in the cost and lead times. Medical is another big area where additive manufacturing is getting very popular, because most of the, let it be from your skull or bone or any tooth or anything, it has a unique design based, it is customized from person to person. So additive manufacturing is the way to go ahead, where it can be customized to individuals, patients' anatomy, and also you can even change the chemistry based on your side effects or your thing to reduce your side effects or something. You can alter the chemistry, you can alter the design. So it's one thing. So one of the small functional robot is the first time fully functional robot was made by additive manufacturing. You just plug in power and it starts moving. The Boston Dynamics is another company where they use additive manufacturing in the latest robots. So as for aerospace, you must be aware that GE is getting big into additive manufacturing. The FAA has cleared 2 parts to be used, fully additive manufactured parts to be used in their engines. There's a housing sensor and the fuel nozzle injector. So this fuel nozzle injector is a very complex design. They have many hidden channels, cavities. Previously, it was like 20 different parts with different suppliers and everything. So now they have come into one part, made it very easy, and additive manufacture was the only way to make it. So the production right now is 1,000 per year, and it's going to grow big to about 40,000 by 2020. Airbus also is getting into additive manufacturing. They're making all the body aircraft structures of titanium in their A350X using the Knox titanium AS system. They can make all these complex shapes, designs and all. So now coming to the comparison of mechanical properties of additive manufactured as compared to conventional cast and rod. I'm just citing for titanium alloy. In general, the additive manufacturing parts have high strength. You can see the strengths are all quite high. This is the traditional manufacturing, but they are low on ductility. It's because again the process has very high cooling rates, so the strengths are higher, the ductility is lower. But once you do a heat treatment, like over here with the heat treated, or if you go to the EBM, this one, or the EBM, because EBM has a powder heating system which is inside, or so the ductility is better. So in general, the properties, they match or they're even better as far as strength is concerned as compared to the traditional manufacturing. As far as fatigue is concerned, fatigue is still a problem because there's still a surface roughness. The surface is not very smooth. So these two are the fatigue cycles for unmachined, like without any final polishing, as built parts. And the traditional manufacturing is given all the dotted lines. Once you finish the surface polishing, I think they match well with the traditional parts. So what it says is additive manufactured parts require some kind of final surface polishing to get a good fatigue life which matches the traditional manufactured parts. So just to give who are the market leaders in adopting the additive manufacturing, it's again Airbus, Boeing and GE, they are leading. There are other companies also are coming on the way. So yeah, I think to conclude my talk, so what is actually required to make additive manufacturing more successful, especially in aerospace and defense also. So all the parts are not suited for additive manufacturing. You have to, there is a specific part whichever is complex design, whichever the number of parts which you may not be very high. So for example, for automotive, where the number of parts are so high, so it may not be that successful. The economics of scale may not work out well for additive manufacturing. But for high mix, low volume kind of manufacturing, the additive manufacturing parts are very advantageous. You also require a skilled manpower because it's a high-tech machine, and also there are a lot of digital technologies involved. We need to put all the quality standards in place for all the parts and the powders. And also to make the additive manufacturing more inclusive or to penetrate more, we need to see the possibilities of concurrent production of additive manufacturing with traditional manufacturing. So you have a traditional manufacturing plant. So, and can you also install additive manufacturing machine to make some parts which are easier manufactured by traditional manufacturing. So like a combined manufacturing place. And also delivery adapted to production near the point of use. So it's also called part on demand or industry 4, which Dr. Satyam was talking about yesterday. You place a demand and you get a part so that it's close to the point of production. And they have to focus on promotion and planning of newer designs, superior designs. We need more focus on this because now we have a way using additive manufacturing to start actually build it. So you have to think more broader to come up with new designs, better way of manufacturing products. Yeah, that's all. I think that's all I have. Thank you.
Thank you for keeping the timeline. If we can permit a couple of questions from the audience.
Yes.
available for even a particular alloy.
Hmm.
So who is looking into that, like an AMS specification body, no?
Yeah,
Looks into
for the
that.
heat treatments also,
No, no.
for
It
heat
starts
treatment
from
there are
powder.
standard.
It starts from powder. Even if I have to purchase a powder with respect to a particular specification, that itself is not standardized.
Which specification, say that again?
If I want to purchase any alloy,
Uh-huh.
like I have an AMS specification.
Yeah, yeah, yeah.
If I want to purchase a 316 powder per se,
Yeah, so even
there is no
the powders,
specification.
even
Yeah.
the powder, the feedstock material, there is also no particular standards on the
Exactly,
quality.
exactly.
And also the product which you make, the standards are not in place. But I think now the companies are coming to make
Okay.
the standards like NIST or under UL, Underwriter Laboratories and all. I think soon it will start coming up for sure.
Okay.
Did I answer your question? I don't know.
Sir, this is Jeevan Kumar from Gas Turbine Research Assessment. We have this machine from EUS. Sir.
Oh, okay.
I was looking for some problems and challenges that we have faced while realizing the critical parts maybe from aerospace.
Okay.
Well, coming to that, as per your knowledge, do you know any of the rotating parts that has been used in aerospace industries as such till today?
So far, I don't think so. Rotating parts are still a problem because you still have the porosity and fatigue issues, I guess, in that.
Okay.
Yeah, rotating parts is still a challenge. Mostly it's static parts. Yeah.
And then, to my understanding, this is almost a decade old technology. Then, what are the challenges where people are being faced? Apart from like what my colleague Shrikant told that, okay, we are not pretty sure what is the acceptance criteria and what is the bottom line to start with the raw material.
Okay.
What I personally feel and what are the challenges that we face is the realization of the part. Can you throw some light on that?
Realization of the
The
part.
part in itself, like the platform getting delaminated, the profile not meeting the requirement.
Okay.
Do you feel this type of problems at your?
Well, there are research issues on this, like how as you said, there is a delamination from layer to layer or something.
I will make it precise. I want to know that what is the biggest criteria because of that this technology is not booming as such.
I gave a list of criteria, which was why the problem. As I said, the acceptance has to be there based on there has to be a standards which has to be placed, and then it has to pass through the testing criteria to meet the standards, and then it has to go through. But I think as far as the quality is concerned, I showed you the strength and everything, fatigue. It is matching well. I think we've also seen in our this one where the strength is pretty good. It's even better than the traditional manufactured parts.
Compared to casting or forgings?
Both.
Okay.
Both.
Thank you.
Dr. Arvind Vadiraj. Okay. He has done his PhD from IIT Madras in the metallurgical and materials engineering. He has got 10 years of industrial experience in automotive OEMs. Sorry. 1 year with Ashok Leyland and 3 years in Mahindra. At Mahindra, he is looking after advanced material technology department and products for the future initiatives. Area of interest are general metallurgy, surface engineering, additive manufacturing. He has got 43 papers to his credits, 5 patents. He has got 1 book to his credit and 2 book chapters. Request him to take over.
Thank you very much. Thanks for the kind introduction. And yeah, I am. It's not on, I think. Yeah, I am from Mahindra and Mahindra, and we have an R&D center, Mahindra Research Valley, in southernmost part of Chennai, about 50 kilometers from the heart of Chennai. We have about 2,500 people there working on product development. We are developing automotive products, especially the SUVs. We hold the maximum market share in SUVs. Yeah. Thank you. What I'm going to present here will be the latest advances in the 3D printing. This is going to be the latest news. I would like to thank Dr. Sudarshan also because he has forwarded me many articles related to this, and many of them would be appearing like this. And my dear friend Srini, it would be a repetition. It will be a little repetition because we didn't have prior communication. this thing. So latest advances, I would love to go forward in this. You see what you cannot print with 3D printing. You can name it, beginning from small structure to the largest structure, including the buildings. I mean, these are few examples to name. Otherwise, you could even build a spacecraft or whatever it is. You see, even you can print the armors, the arms. A while ago, there was an article. The Western governments were very scared to see this 3D printed pistol, because all you can do is send an email or CAD model to the America and get it printed there, rather than sending a physical models. They may even print missiles and bombs there, and they can even explode there if they had an intention to induce terror there. I mean, to that degree, the additive manufacturing has penetrated. It is a very, very novel field, and thanks to Srini has given complete introduction, and it is foundation is set so that I can go forward from there. Even drones and even soldier boots. I mean, it has penetrated all segments, even the food, the medical field, such as even building organs. Back in 90s itself, they were making organs, human organs, even blood, veins, so many things. Textile industry, the food industry, everywhere it has penetrated. Now going forward, this is a little different from what Srini has shown. Another J Group Robotics, another report, they predict it's going to be $20 billion. I think, no, sorry, $8 billion industry in 2019. And you can see the growth rate, it is 55% CAGR by revenue and 63% by volume. Such a phenomenal rate. I mean, you don't have any industry which is going that way. You have around 20,000 companies across the globe in about 150 countries. And if you see in India alone, we have 350 companies registered, about a $79 million expected revenue in 2020. And it is gaining a lot of momentum, especially in first three areas, that is aerospace, medical and automotive, and of course something in education, consumer goods, etc. And wherever the large number of good amount of customization is required, you'll be this is the best manufacturing process, as we know. If you see in Indian market, primarily it is in, as I told you, automotive, electronics, and rest of the others. See, with regard to automotive, Mahindra itself is using this technology for the last 15 years. We have been printing some small parts and looking at the fit and the form for certain parts and things like that. So this is an air intake which has been made by 3D printing. This is by CRP Engineering and Magnetic Merolith both together. See, you can also save weight. You can check, you can do a lot of analysis prior hand. Before release itself, you can do a lot of testing. The fit and form and the surface quality, etc. I mean, how whether the lot of iterations. This is what it is. A lot of iterations can be done in this. When we have been doing this last 15 years, we have a machine and we have been doing this. And this is just parts, automotive parts. But if you see, the whole car has been printed. At least 50-60% of the parts here is printed part. This is RB2. At least 10 examples you'll find in the public domain of 3D printed cars. And especially the Rolls-Royce and BMW, they're using even functional parts, interior parts. This is more than 50% of the parts are printed here. And then you see this particular car is so lightweight, it can go from one coast to another coast in the US with just 10 gallons of fuel. It's such a small amount. And second example you see is an autonomous vehicle. It is 12-seater bus. Here also more than 50-60% of the parts are printed. It's a 12 people's capacity bus. And this bus can be bought to your home on an app based. Just like you order Ola and Uber here, a taxi, you can order the bus also there. This is undergoing a trial run in UK. And you see, the parts are printed in just 10 hours and assembled in 1 hour. This kind of production time, you don't find it exactly in our conventional manufacturing also. And another example is a 3D printed stainless steel bike. The entire web structure, what you see, is stainless steel, and it's printed layer by layer with the stainless steel blobs. And you can make such a good designs. You can customize it very easily. This is one area you can customize, because in the area of this non-motored transport, you don't have rules. Because in case of a car or bus, or in case of a bike, you have CMVR rules. You have to stick to the CMVR rules. You need a license. You need a license plate, license registration, everything. But in case of these things, you don't have registration license. You can make any shape, any length, anything you want. So a lot of customization is a possibility in this area. And this is done by one university, Delft University. Next is titanium jet structures, which you need to exactly. The one thing which I didn't see is the cost saving, which is about 2 to 3 million per aircraft, which is a saving just by making this part, which it was not there in your presentation. And it's done by rapid plasma deposition. Of course, this is aerospace is one area where you can customization is very on demand, you know. And this is the largest printed 3D titanium part, and you can see this size, inches, 19 inches. It's a very large piece with the titanium part. And one thing fascinating is this part is printed in room temperature. How they can print in metal part in room temperature and how do they do, we do not know. Probably using binder technology, yes. But probably sintering is required after that or whatever it is. Otherwise, it's difficult. That's what I was thinking. So this is the largest part printed so far in the aerospace sector. And if you see another thing is the cabin partition. These are also printed. They've developed a special alloy called scam alloy, which is about 45% lighter for 3D printing purpose alone. And they've done around 10,000 iterations to get this part. So next time when you go in the flight, probably you will see this cabin partitions. Currently it is an Ultem material, that is also aircraft material. And you can see how large these printers are today. You can print from small chair all the way up to the buildings and mega structures. In the right bottom most you can see you can build buildings also. Yesterday I visited one company, he was telling I can, within a matter of hours, 2 hours or 1 hour, you can print a whole 2 BHK house. In China they've done it. So to that extent 3D printing is penetrating. And you can see this is a 3D printed bridge. In one place in Netherlands, they have 60 miles of canal. I mean, there is no way you can just go from place to place. You have to build a bridge. So here, one company which is a furniture manufacturing company has developed a robotic welding robots. They're using welding robots and printing the bridge. The bridge can be printed from one side or 2 robots from the other side and they can join in the mid. So it can, within hours, it builds the whole bridge. That's the this thing. And if you see this mud extruding 3D printer, this is from I think WASP in Italy. They take the raw material, which is mud, clay and natural material mixed together, and they print a very low cost housing for you. This is another innovation which in the poor parts of the world, probably in the very underdeveloped nations, it is going to be very useful. 20 feet tall and is capable of printing structures up to 10 feet. 2 people and 2 hours. That's what it is required to print this, nothing more. Can extrude mud, clay and even natural fibers, which are all natural materials available anywhere across the globe, you know. And this is very fascinating. You can print metal parts in mid-air. And this video I saw, it was very, very fascinating. See, there are some kind of 3D printing pens which are available, which you can use it and print some structures just like that. But that is a plastic, that is for fun and that is for plastic casing. But here, it is metal. They're using a silver particles in ink. And they're ejecting through the nozzle and they're passing a laser, very fine laser at the nozzle tip, which immediately melts the silver and attaches to the part. And immediately you can get a mid-air structure like this, which is like a butterfly and things like that. So probably in future you can build these building structures also in a mid-air without any support, you know. So these are all university researchers. I think this is Harvard Main University. And the next thing is from University of Bristol, yeah. So this is the composite part which is printed. So while printing in a laser, what they've done is they've passed an ultrasonic inside the material so that the fibers, that is carbon fiber which is there in the material, gets aligned in a particular direction. Wherever there is a low pressure, that aligns to the opposite direction and gives the strength in the direction. Typically when you make a composite part, it is very difficult to get the alignment of the fiber, especially it's a chopped fiber. In a long fiber, fine, you can align it, whereas in a chopped fiber, it is very difficult to get a proper alignment of all the fibers so that we can give strength in a particular direction. But here, just by ultrasonics, they're able to give direction to the particular fibers and they can give a strength in the direction. So that's what it is. And it's a 3D printed midsole. See, some of the athletes, during different workouts, they have to switch shoes. So instead of switching shoes, you can switch the sole here. Keep the same shoes and switch the soles. So according to many, some analysis has been done by architects. So they can change the shoe sole and according to the need of the workout. So one particular workout need one type of sole, another particular workout need another type of toes. So 3D printing is very much possible. This is a typical example of a customization. The next thing is much more fascinating. This 3D printer is of the size of your tiffin box. It's like a tiffin box you can carry in your backpack. See, this, you can print the object through your smartphones. You can insert your smartphone in the bottom there, and you can fill the chamber with a photosensitive resin. So one app which is downloaded in the smartphone will show different colors, and the light which comes out of the smartphone is going to print your object. It goes from top to bottom. And if you see, this has only 3 plastic pieces, 1 chip and 1 motor, that's it. And less than half a kg, that is about 780 grams. So built by an Olo. So these are fascinating innovations that has undergone. And this is, of course, what we said, 3D printing using a binder. You print with a metal and then sinter it. So what that professor says, Ramil Shah, the professor says it is also cost effective. It is also effective. It is not that sintering has to happen along with the printing, metal printing. Even printing and sintering also is cost effective. And the next thing is not using plastic or not using laser. It is by ultrasonics. Printing the whole part, layer by layer. You take different layers of metal, make it, keep it one above the other, and then pass the roller with the ultrasonic input in that, ultrasonic waves. So this will bond the layers, give a very strong metallurgical bonding, and produces a very strong sheet layers. So this is another innovative way for producing a 3D printed part. It can be aluminum, copper, stainless steel, even titanium. So all these things. This is another, 5 more minutes, I'll finish. This is another fascinating. If you want to gift a ring to your beloved ones next time, you can just speak over and record it for 3 seconds, and then that thing will become a signature, and it gets printed in the form of a ring. It can be a gold, it can be platinum, it can be stainless steel, it can be 22 karat gold, anything. Just 3 seconds. This is a Japanese company called 3D Wave. They have come up with this fascinating idea. It costs about $130 to $1,300 depending upon the material used. But this is one fascinating idea of that. And you see there are, apart from hardware, even the software is important for printing. Beginners like me, if you say, I need something to drag and drop and then add software files and to print it. So you cannot expect me to learn CATIA, learn AutoCAD from the beginning and do things. But here, the Scratchy CAD, you can use this software to, even children can use it. Just drag and drop and make a model and convert it into STL file and then print it. So that easily they have made it. The next thing is adding one more D to the 3D printing. The concept is very simple. You print the part, and once you trigger that particular part with either the light or electricity or heat, the part changes the shape. You can see in the bottom there how it has changed, that flower. So just by putting in the water, the shape changes. This is very useful. This kind of concept is very useful when you have, let's say, biomedical scaffolds or something, which you can print it outside and put it inside the body, and it can take the shape of the body because of the bodily heat. So this is called 4D printing from now on. Just like you have 3G and 4G, India is not ready for 4G also, now 5G is getting ready. So like that, in 3D itself is not penetrated yet much to the market, now 4D is getting ready here, in several universities. And I think that's all from now. Thank you.
Thank you for your very good lecture and very interesting. If there are questions, we can have 2 of them.
Nothing? Yeah, please.
Sir, as per your experience in Mahindra and Mahindra, to realize a part of 200 mm diameter, for example, if I take a cylinder piece, how much time it will take to realize a part under additive manufacturing?
Cylinder piece is
200 mm.
Cylinder block.
Like 200 mm length, or take for example 50 mm diameter. How much time it will take as per AM?
See, printing 3D printed parts in
metallic part.
Metallic parts, that's difficult to tell because it depends on how much accuracy you require, what surface quality you require, what post operations you want to avoid, all these things.
Does that mean that through your process you can control the surface finish as well?
It is possible when you have a very fine control on the process, movement, the particle size.
Okay.
Those things. And post operation is necessary.
Okay.
Sipping, and then heat treatment. All these things are necessary.
Why I asked you a question because you have shown some slides where you claim that China is able to build a 2 BHK flat or bridge within an hour.
Yeah.
To my understanding, even building a cylindrical sample of this size will take more than 8 hours.
Now, you see, for building you require don't need a micron accuracy.
True, true.
So several millimeters of gap also is probably okay
True.
for them. Probably they have improvised something. I do not know exactly what.
Yeah.
I didn't get much details, but they have done that. But printing parts, it's many hours actually.
Yes,
I've seen 13 hours.
yes. I have my personal experience that if we build a single turbine blade
Yeah.
of what size I have told you, it takes almost 8 to 9 hours.
Yeah, printing alone.
Yeah,
Printing alone.
I have a
Post
percentage of 2 microns.
Yeah.
Thank you.
Thank you.
Speaker, Mr. Nayan Patel, of AMSC, he's AMSC manager for Renshaw Metrology Systems. He's a graduate in mechanical engineering in automotive design from Brunel University, UK. He has been working for Renshaw for 18 years. He has been working with various divisions for manufacturing to design. He graduated in 1996 and progressed to sale leader for which assembles high precision equipment for CMM industry. He got opportunity to work as one of the design team for spectroscopy division, Raman Instruments. In 2000, he moved to USA with Renshaw to work as a CMM application engineer based in the suburbs of Chicago. After 3 years in USA, he moved back to UK, working as a global product manager for the CMM division. Since 2009, he has been posted in India. Working with Indian sales force to develop business and support activities. He has set up Renshaw Additive Manufacturing Solution Center, spearheading Renshaw's first global AM Solution Center. I'll ask him to.
Just give us a minute, we're just setting up the projector. Good morning, everyone. Sorry about the delay. As we've heard from our colleagues, additive manufacturing is bringing a lot of disruption to the industry. I hope during this presentation we can give you some idea of what the industry is trying to do, or particularly Renishaw is trying to do. Before I get into that, just to give everybody an idea of what Renishaw is, Renishaw primarily is a metrology company. It's a global metrology leading company. Last year we did nearly £500 million as turnover. We have nearly 4,000 staff. What I'm trying to talk about today is how we have interpreted additive manufacturing, how we intend to deploy it for the industry. So, as we've heard from our colleagues before, you see here we got a design, we've got process validation and process capability. Unless we tick all these boxes, we are not going to get a viable product at the end. So today, as we saw from the previous presentations, additive manufacturing is being used and considered with all the listed items here, from research, prototype, weight saving, plastics, etc. What we've done is we've broken it down into different layers, what we've like to call levels or a staircase. The first one is rapid prototyping or tooling. This is where we normally say everybody is considering it today. Some people are more advanced than others. Most people only consider this technology for rapid prototyping or tooling. The next step onwards is direct part replacement, okay? Where you may have a process which is obsoleted, you can't make that old part, so you use additive manufacturing to do that. The level above that is what we call part consolidation. I have examples to show you what we mean by all these, by the way. But the ultimate use for this technology, we believe, is actually designed part for additive manufacturing. It's unfair to take a traditional part which you manufacture in a factory and say, make this in additive, it'll be cheaper. That's not what additive manufacturing is. Right, so as I said earlier, if you look at the financial benefits, because everybody wants to know about financial benefits, okay? So as far as the staircase is concerned, if you look at the bottom where it's not a real good use for this technology. The benefits are low. Production benefits are low, the lifetime benefits are low. The more you move up the ladder, the more benefits you have, okay? It means the material usage is better, so your cost is less, shorter process times, etc. But look at the lifetime costs. Weight is definitely important because weight is definitely more important because most of them are aerospace parts today. Faster production launches, we're helping companies to reduce their prototype life cycles from many months to 1 or 2 months. Product reliability is one thing because you can actually design much more, with less compromise, performance, etc., etc. As I said earlier, AM is brought a disruption to the industry. Everybody wants a piece of this additive manufacturing, but what are they going to do with it? This is what we're finding. So it allows you the listed items. So the design freedom it gives you, the precision, automation. There's a lot of things this technology gives you, but how do you employ it in your process? Okay, you have to buy a machine. There's a lot of machines which have been bought in the industry. Not many people know how to use them or what to do with them. So what we believe is we want to educate the customers as the process goes on. So going back to the staircase, the first one, the prototyping and tooling, I've just shown you some examples here. So if you look on your left-hand side is a typical part which we get asked to make because they make it today in a normal process. Can we make it here? Conformal cooling is another application where we are finding that this is a very, very useful technology. Why? Because you can build in cooling channels in your injection molding. Now, you may say, but I don't need my injection molding to last that long because things change every year. But this gives you better parts, it gives you better finish, and also quicker release time. So there's many different advantages. So next level up is the direct part replacement. So on your left-hand side, you see a typical example of the usage of material. So to get the part in the center, you would have to use, from a subtractive point of view, nearly 5 kilos of material, where the parts which you've machined cannot be reused again. Where on the left-hand side is the powder, which is just over 1 kilo. You machine a few hundred grams away and you end up with a part. So usage of material is much more efficient. Part consolidation. This is also a very interesting application. We do a lot of work with microwave guides. Microwave guides are traditionally they're actually a very simple part, but their application is very complicated. It's a very complex shape and traditionally made out of many different pieces. Because of its application in terms of microwaves, these joints have a disruptive effect. So in additive manufacturing, you can design in one piece, okay? As far as mechanisms are concerned, we've been approached by consumers, where can you make some jewelry out of titanium, etc. So those things have also been attempted. However, this is where we believe the true potential of additive manufacturing is. So this is where the freedom of this technology can be realized. So if you look here, we call this a hollow part. This is a real-life example of a part which we were given by a company, and they said, can you optimize this in terms of weight? Okay, so it shows you on, I don't know if you can see that or not, but it says 620 grams. When we started with that part weighed 1.5 kilos. Okay, this part physically, mechanically is the same shape, it gives you the same performance, but it's less than half the weight. Okay, so it's a real example of additive manufacturing. Next level up is topological optimization. So again, if you see in the center, there's a squarish bracket. Another company approached us saying, can you do something about that in terms of saving weight? It's also space critical. This is actually going up into space. Can we reduce the actual amount of volume you use? So when you put it into a computer, you get something what we call fingers of faith. When you take that to a normal manufacturing shop, they'll say, how do I make that? Okay, so additive was the answer. Then we also learn about applications. One of the things we've learned recently is increased surface area. Many people would say, why would you want to do that? Well, to dissipate heat, or the other way around. Because there's a lot of technologies out there, a lot of electronics nowadays generate a lot of heat. How do you get rid of it? So additive is helping when you can manufacture effectively as the next slide says, metal foams, which allow you to dissipate heat very, very quickly. We also work with a company called Hyeta in the UK to specialize in heat transfers. This company traditionally made a lot of complex structures to allow them to dissipate heat, but they could never make them until additive came along. Okay. Another example of a bike, and this is a company called Empire Bikes in the UK, where you can actually order a bike. We make it in titanium. They assemble it into a full-blown bike. Okay, customization. This is something I'll come on to in a minute, but customization in terms of medical is a huge, huge potential for additive manufacturing. So let's just go through a very common problem. So this is a company which approached us. They have a manifold requirement. It's a weight limited operation. It's basically high pressure, and it's got some solenoid valves and some outlet ports. But let's look at it in terms of design space. If you look at how much freedom you have to design. So if you direct part replacement, going back to the staircase, you don't really have a huge amount of design space. It's just, everything is the same, it has to be the same, just make it. The other one, adapted for AM, you have a little bit of freedom because maybe the angle of the pipe changes, etc. Design for AM means that it's a clean sheet. You can do what you need to do, okay? The effect of that is huge. So if you look in here, the left-hand side is direct part replacement. So we make exactly the same part in AM, okay? Which incidentally weighs 4.6 kilograms, right? And then the adapted one, so we have a bit more freedom to remove material, etc., weighs 1 kilo. Then the design for manufacturing one, if you see, looks completely different. That weighs 400 grams. Now, look at the other advantages, is the one on the right-hand side, maybe if it's packaged correctly or better, it improves your serviceability time, accessibility time, etc., etc. One thing to point out, just go back. This is what the advertising promises as far as the additive manufacturing world is concerned. This is what you get in reality, okay? So it's not an island. There are processes which are involved to finish off the products. It's not a black magic box, but we're here to tell you that it's it's not magic, it's real. So what Renishaw is trying to do is they're trying to lower the barrier of AM. AM technology is not cheap, okay? We know that. We've done a lot of research, and what we're trying to do is we have set up additive manufacturing solution centers around the world, okay? And I'll talk to you about them, what we're trying to do. It's a global network. India is the first one to be established in Pune. Application expertise worldwide, we have almost over 100 engineers who are dedicated to application engineering for additive. Our main business is integrated manufacturing, so we understand manufacturing very, very well. To give you an idea, these are the locations of all our additive solution centers. So as I said, Pune was the first one, and we have Shanghai, Stuttgart, etc., etc. They're all going around the world. They will all be open by the end of this year. Okay. So let me talk about the Additive Manufacturing Solution Center. One of the first things we are offering, even in India, is what we call an incubation cell. Now, as a company, if you say, right, I want to try additive manufacturing, so how do you do that? Well, you go to a service bureau. Service bureaus are very good. They will typically do exactly what you ask them to do. But what about, how do you design this? Can I do this? Can I optimize some parameters? Do that? Can't do that, right? What we do is we will rent you a machine in a room, and you can experiment. You can have our help, or you can lock yourself away in that room and do what you need to do with that machine. Okay? So this is a concept we're introducing to you guys to lower the barrier, because initially, look at the costs of buying a machine versus renting a machine on a monthly basis. It's far cheaper. So attached to the incubation cells will be offices, pre-production, which we don't have set up yet in our Pune office, powder management, finishing, heat treatment, which we talked about as well, post-processing in terms of machining and CMM inspection, and most important is materials lab. In the industry, we find that as soon as you mention additive manufacturing is printed, people have a doubt. that what's the porosity, what is the composition of the material when you finish with it, etc., etc. So as Renishaw, we will give you a physical verification of the part and a metallurgy verification of the part as well. As far as the Indian facilities are concerned, it is the first one to be opened in June. We have 4 machines there now running. We have the finishing, the metrology, all the services available. We've developed a lot of local suppliers to do a lot of the post-processing for us. Some of the things we don't have or maybe too expensive to do, so we get it done outside. Okay? And we also have a capable engineering team. So what have we done with this industry? What have we done with additive in the industry, sorry? Healthcare, aerospace, automotive, dye and mold, oil and gas, consumer. They're all our customers today. Can I just point out in healthcare, we have a 13485 approved laboratory in the UK running, making medical components. Okay, so that's a big tick mark for the additive manufacturing world, that there's medical people are accepting parts made in additive. More examples, Moog is one of our customers for many other products. They have our machines, they are actually making this component, which is airworthy, and I forgot which Airbus it is, but it is in one of the Airbuses as one of the primary actuators. Okay. Delphi, so if you look on your left-hand side, this is the component we started with, which is 2.5 kilos. We optimized it, and it less half the weight. But it's not just the weight. You look at the part, we've managed to include a lot more sub-assemblies within this component. So overall, the component count is actually reduced as well, which in aerospace or any other world improves reliability, stocking costs, etc., etc. Okay. Sorry to put a graph up on, but I had to do this. So this is the oxygen level and nitrogen level content of titanium powder. In titanium alloy, there are 2 grades which we deal with, grade 5 and grade 23. Grade 23 is the one we should be using for medical purposes. Okay. Now, if you look there, we have developed an optimized heat cycle which will allow you to produce grade 23 ISO 13485 components in our system. So the system does not do anything to the powder, it keeps it as it is. Okay. So what does that all mean? Well, what we're trying to do is remove this word additive. We want to call it just manufacturing. This is our vision, this is our goal as a company. That's what I'm standing here and telling you guys. That's all I have to say.
Thank you so much for keeping the time and giving us a very snapshot view of the additive manufacturing. If there are a couple of questions, we will permit that. Please.
You have shown some of the hollow parts that you are making.
Sure.
What type of mechanical test you have done, or whether these parts are dynamic in nature?
Are they what in nature?
Are they rotating in nature?
No, they're actually mounts.
Okay.
The testing was not done by us, it was done by the company. They will not give us all the data because of NDAs. But
okay,
they have
then just in either in 50-50, whether those tests were compressive in nature, or you have done extensive tensile test as well?
tensile strength. They've done all the tests, including vibration, because they're engine mounts.
And then coming to your support services with respect to the machine that you said that you can provide on rent basis. What I understand that these products, this machine comes with not only with the alloy base, it also comes that these are the precise grades that you can use. Say for example, if I'm using EUS M280 machine, it comes with only certain grades like 718, 713, these are the grades I can use. With your machine, can I explore different materials of the same superalloys?
So there's a key advantage to our technology is that we call it open parameters.
Okay.
So we don't lock any customer down to saying you have to buy our powder. If you can source the powder cheaper or a particular alloy you want, then we will help you to develop the parameters for that.
Oh, that's nice. Thank you.
Okay.
Hello. Yeah, my question is slightly different from the manufacturing topic as such. So I would like to know, Renshaw does have work on laser cladding applications also.
Laser cladding?
Laser cladding.
Sorry.
So we're not into that.
Thank you. By Mr. Janardhan Rao. He's from John Deere Technology Center in India. He's senior technical specialist and an SMA member. He has done his B.Tech from Osmania University and M.Tech in tooling design in Central Institute of Tool Design, Hyderabad. He has got 8.5 years experience and in design, tool design as well as additive manufacturing. Over to you.
Yeah, no issues. Okay, so today my topic is design for additively manufactured tools. So here in this topic I will not cover about the technology because technology is already covered by my previous speakers. Okay, so agenda of my this topic is first I'll let you know like what is tooling. So okay, what type of tooling means, what it applicable, what type of stuff it is applicable to. Typically, what are tooling characteristics, and how additive manufactured evolved for tooling, and why should we use additive manufacturing for tooling. Okay, so what's some design considerations for AM tooling, and what are the AM materials available for tooling. Okay, and I'll go through some of the examples from the industry or from our own industry, my own industry. So some of the deciding factors for choosing between conventional and additive manufactured tooling, and also what are some AM tooling benefits, current challenges, and maybe at last summarize. Okay. So who don't know about tooling? Tooling is a manufacturing aid used to produce specific product or a part in a batch or in large quantities. So under tooling you cover like you get jigs, fixtures, gauges, dies, molds, cutting tools, patterns are all part of tooling. Okay. So what are typical tooling characteristics? So to manufacture any tool, you require skilled workmen, okay, or tool makers, or normally is done in a tool room, okay. And most of the tooling involves complexity, and also tooling is produced in low volume, okay. And for manufacturing any tooling, you require multiple manufacturing processes, okay. And a tooling is specific to a particular product or a process. And also like to manufacture a tooling, it takes months to weeks to months of time. So it's a high lead manufacturing lead time item. So how tooling tooling was done through additive manufacturing, how it is evolved. Okay, so if you see like the first additive manufacturing part was something done in 1980s. Okay, then it evolved for making the concept models. So concept models is something like having a physical part but not for actual practical use. So it's only for visualization or only for your marketing purpose. And in early 2000s, like they started using for functional prototypes. So functional prototypes means you print the part and you're using on your vehicle for testing or some other purpose or fitment purpose. Okay. So from 2010, like now, they started evaluation of additive manufacturing beyond prototypes. So beyond prototypes means like for tooling or for low volume production parts. So why should we use additive manufacturing for tooling? So what are the advantages basically? So one main advantage is you can reduce the weight, okay, and you can minimal processing. So for manufacturing a tooling, what you typically do is you produce the child parts, basically sub parts, and assemble them together. But through additive manufacturing process, maybe it can be made in one part. Okay. Another is reducing lead time. That is one of the main things. And also like complexity, You can produce, I mean, in additive manufacturing, simple or complex doesn't matter. It's one and the same in additive manufacturing. So that is one of the added advantage, and in some cases reduce cost, okay? And also you can get more improved ergonomics on your tools. So some of the design considerations for AM tooling. So whenever I'm designing a tooling through additive manufacturing process, first thing I need to know is like what is the machine capability, what are its specifications. Then next thing is the cost driver. So as you know, like additive manufacturing is a costly process, okay? So you need to design for a minimum material and minimum build time, okay? And also without compromising on the strength. And also if you have to see if you can minimize the number of parts, okay? If you can consolidate the number of parts and make as an integrated structures, okay? And also you need to see like if you can design for self-supported structures. It's like, I mean, as I said, in additive manufacturing, material and the build time has the main cost parameters there. So if you can see, I mean, in additive manufacturing, if you have some shapes which require support material, you should try to avoid that. So here a typical example, like I've shown you a hole. So if you want to make a hole, if you see if you can make it a pear shape, so that, I mean, you can avoid support material there. And also if your tooling is subjected to wear, especially in this is in case of a plastic tooling or a polymer one. So provide metal liners such as bushings, wrist pads, okay? And as you know, like additive manufacturing, the accuracies are not that good for if you want, if your application is of a precision type, then you may have to add finishing allowance in your whole surfaces requiring precision. And also if you can see, like if you can add a function to your tooling, like I mean you can do lightweighting, you can do some ergonomics, I mean give ergonomic features on your this thing. And also like in additive manufacturing, one constraint what we have is strength in the Z direction. In the Z direction, normally the strength is 30% lesser than the XY direction. So you have to orient your parts for printing in the XY direction if you require strength in that particular direction. Okay. So these are some of the materials available in additive manufacturing, for additive manufacturing in metals, okay? But for tooling, mostly we use maraging steel, okay? Is like a high nickel alloy steel, and also we use stainless steel in metals. And in plastics, we use the FDM process, and normally like in FDM, we use, these are the materials available, okay? ABS, PC ABS, polycarbonate, ASA, nylon, Altem, ABS and ABSI. So for tooling, we use normally polycarbonate, nylon and Altem. So we use Altem material for weld tooling, where this material has the highest FST ratings. So it's like it doesn't send fumes for the weld spatters. So that's the reason we use this material for weld fixtures. So I'll go through some of the examples what we have done using the additive manufacturing process. So this is a spring installer. So conventionally, if you see above, that is the conventional tool what we have, okay? So it's basically a bulky fixture, okay? You are placing the part there, and you are putting a spring there and assembling it, and you have a lever where you pull the lever and the spring gets assembled into the part. So with additive manufacturing process, we are able to design a tool, and you can see that at the bottom, okay? It's like an odd-shaped tool, but this can be possible only by additive manufacturing process. If you want to do it by conventional process, it may be very difficult, okay? So you can see a bulky fixture to a small tool, okay? So this is a customized torque tool insert. So basically, we were using 3 different types of torque inserts for our torquing hydraulic hoses. But with additive manufacturing process, what we are able to do is we are able to combine all these 3 torque inserts into one and able to print that. So another advantage is like the lead time reduction. Like a supplier quoted for 5 weeks, and we are able to get it designed and printed in a week's time. Okay. And also, particularly in this case, this is 30% cost, cheaper than the conventional process. Okay. So next thing is this is actually a check gauge for a sheet metal part. This is almost like a 500 millimeters big part. So conventional process, you can see like on the top right hand side corner, it's made of sheet metal. basically that gauge was cut by, made by a laser cutting process, held together by a slot and tab mechanism, welded together. And the main challenge is here is the weight. So weight of the tool is almost like 10 kilos. Okay, so this tool normally, like the gauge is normally what the operator does is whenever there is a batch change, he takes that gauge from the rack, inspects the part for the first couple of parts and put it back to the rack. Okay, so the thing is here the main is the weight. So you want to reduce the weight. So you can see at the below. So we have done through the printed that in in plastic, basically. That was printed in polycarbonate, and also like since there is a metal to plastic contact, so we want to increase the durability of that tool, because plastic wears out very fast when it comes in contact with metal. So we have provided metal liners there, you can see there. So with this we are able to reduce the weight from 10 kilos to around 2 kilos. Okay, so that's what the advantage we have with this process. So this another example is actually a template, again similar template. This is for our mower deck. Okay, so you can see at the top the conventional process that was made in FRP, fiber resin plastic molding process. So here the challenge is whenever we have some product or process changes, that has to be scrapped because you cannot do anything with that. So what we have done is we have actually made that into segments and used the 3D printing process to manufacture it. You can see on the left side, it's made in segments and joined together by we have given some self-locating mechanisms there, and they're joined together by some angles. So in here the advantage is whenever there is some product or process changes, like we can just remove that segment wherever the changes are there, and you can replace with a new printed part. Okay. And also here we have some advantage on the lead time, manufacturing lead time, and also on the weight side. Okay. Now coming to the complexity, I said complexity is one of the factors which you should consider while for 3D printing. So this is a tool for a hydraulic hoses assembly. Okay, so this tool is used for aligning the hydraulic hoses before going to the main assembly line. So the thing is, like you can see the complexity here involved. You cannot expect such kind of stuff will be manufactured by a conventional manufacturing process. But for 3D printing, it's possible. You can see the 3D printed tool at the bottom. Okay. So this is another example of an assembly fixture. Okay, so this assembly fixture is for assembling the hinge to a door panel. So in the top side right hand corner, you can see the actual conventional one. So it was made of steel. Okay, so and is assembled together. So this same was converted to additive manufacturing this thing. So here the advantage is the processing time. So this fixture was made in 4 days time. Okay, again wherever it is coming in contact with metal, we have given metal liners and stuff. So main advantage here is again reduced weight, lead time reduction. Again an example for a instrumentation panel assembly fixture. You can see on the top side that is actually this fixture is used for assembling the instrumentation panel. So the fixture, challenge here is like this fixture has to accommodate around 5 variants, 5 different models into one fixture, and the fixture is pretty big. And the thing is, batch volume is very less. Like maybe 10 in a batch, they may be producing only 10 parts. Okay, and the thing is, after every this thing, they have to move the fixture out of the assembly table. So here the main requirement is a lightweight, and this fixture is almost like 900 millimeters long, 900 by 600. It's a quite big fixture. So weight is a main challenge here. So we have and also it has the part has complex profiles. So to manufacture that complex profiles by a conventional process would have been difficult. So we have designed a fixture, you can see at the bottom, and what we have done is, like while printing, we have chosen in 3D printing we have a feature of a lattice. We can give a lattice or a weight for weight reduction. Basically we call it the honeycomb or lattice. Yeah. So we have used that feature and able to reduce the weight by almost like 60%. And also this was printed in around 3 days time. So I mean, if you want to do it conventionally, it would take at least a month's time to get it, but we are able to do it in a 3 days time. Okay. So again, this is an example of a weld pick-off tool. So you can on the right top corner, you can see that is the actual tool. So the challenge here again is the weight. It's like it's weighing around 4.5 kgs. So we are able to convert that to a additive manufacture tool. Now it's like weight is only like 1.3 kilos. Since it's a welding fixture, we used a material called Altem. So again, as I said previously, like this material is a weld spatter resistant material or having highest FST ratings. Again, here you can see like wherever the part is getting in contact with the tool, we are given metal liners for the durability purpose. Again, a weld pick-off tool, okay, printed in Altem with some metal liners. And here you can see we have given a reinforced carbon fiber handle. Again, that handle also was printed in, is 3D printed. Okay, so it's printed with chopped carbon fiber. This is a stud welding fixture. Again, here the challenge is the weight. So we're able to reduce the weight by around 75% here. Another example for kitting trays, shadow boards. I think in our assembly lines we use kitting trays and shadow boards. So basically we'll take made in nylon stuff and we do the CNC milling to get the profiles. But we used a 3D printing process to do this. We have done it on a low cost printer, this one. So to get the savings, since that application is not critical, we have done it on low cost printer and they were able to save the cost by 50%. So this is an example of a mold. As you know, like for making any plastic parts, we need a mold. Okay. So in this particular requirement, my requirement is only like I need 100 parts. Okay. So we have printed the mold on a polyjet machine. Basically, it's like a polyset, thermoplastic material, and we're able to produce almost like 100 parts, and still the mold looks new. Okay, so here the advantage is if I want is the speed. This was printed in only like 2 days, but if you want to manufacture this mold using a conventional process, it would take months time at least. Okay. So this again, this is not example from our side, but it's like external example. But who are all in the mold industry knows like the importance of conformal cooling. Okay, so this type of cooling channels can be possible only by additive manufacturing process. So what the advantage you have, it reduces your cooling time, the mold cooling time, and when you have when the mold cooling time is reduced, the productivity increases because because you can reduce the time between the shots. Okay. So these are some of the examples. Now, what are the deciding factors from going to conventional, whether you want to manufacture the tool by conventional process or additive manufacturing process? What are the factors? So one is the cost, accuracy, durability, complexity, internal features, lightweight, ergonomics. Now, you need to have a trade-off between these parameters. Like you may want to have a tool which is like lightweight, but cost is more. So which one is important to you, whether you are lightweight or cost? So if it's lightweight, then you go for additive manufacturing. If it's a cost, then you may have to go with conventional process. So you have to do the trade-off between these factors. So with this, so what are the AM tooling benefits? So one is the reduced weight, innovative designs, cost effective for low volume parts. Basically, you may require only like 1,000 parts in a year. So this may be a good thing. Reduced manufacturing cost. Again, this is region specific and complexity involved. So if you want to have a additive manufacturing tooling in US, it may be cheaper there, but in India it may be costlier because conventional processes are cheaper in India. This 3D printing advanced technologies are costlier in India. Okay. Reduction in design efforts, because in 3D printing I don't require any 2D drawings, I just require a 3D model. So that reduces my design efforts. Part count reduction, I can print structures in one structure and I can build structures parts in one structure. Reduced design limitations, because when you do it the conventional process, you have to consider the conventional machines what you have and you have to design for that. But here I have a design freedom. Minimal inventory of tooling spares. I don't need to maintain any tooling spares, because if I have anything broken, I can print it and use it. Okay. And as I said, complexity comes for free, and also you can use high value materials in an efficient way. Okay. So along with the advantages, we have some limitations also. What are the limitations? One is the speed of build. 3D printing is a very slow process. It takes a lot of time to build, so that is one. And materials are very expensive, okay? And durability is a challenge in case of polymers, okay? Accuracy and tolerances, that's another one. And as I said, Z direction strength. So since additive manufacturing is a layer by layer manufacturing process, in the Z direction, in the build direction, normally the strength is less. Surface geometry may be sometimes issue. Material properties, because we have very limited range of materials available in additive manufacturing, so that's one of the challenge. And also, like for metal printing, the machines are very expensive. Machines and materials are very expensive, and also the process is you have to take a lot of care because it's hazardous. Okay. So this is my last slide. So for any organization, I mean, if you want the AM tooling to be successful, what are the things we need to take care of? Okay. So one is the first thing is identification of right application for AM tooling. So you cannot take any tooling and say just will produce by additive manufacturing. So you have to select the right application. And another thing is you cannot design something for conventional process and use for additive manufacturing. You have to design for additive manufacturing. Okay. And another, of course, you have to select right AM process and material. And also another thing is the education of end users. Like ultimately your tool will be used by in the shop floor. So operators should be well educated on how to use those tooling. And of course, this is whenever you introduce a new technology, there is always a resistance on the shop floor. So there should be a push from the top management. So with this, I conclude on the additive manufactured tooling. So the unique features of additive manufacturing make it attractive for tooling industry in both plastic and metals. Okay. You can see large savings in both tool cost. Again, this depends on the complexity and the region which you are in, and also it can help you increase the productivity. So still we have some hurdles in the knowledge and design to achieve the full implementation. Okay. Thank you.
Thank you so much. If there are questions, we'll permit two, and maybe during the after the session is or during the tea time, others can ask the questions.